Hi, Professor Mel, and anyone else who might be watching. My name is Drew Els. I'm a junior in the Systems Engineering Department,
My name is Ian Taylor. I'm a senior in the Mechanical Engineering Department.
and this is our final video for Robotics Laboratory, ESC 447. What we're going to do is just talk through the different elements of the project that we've done over the past semester. We're going to cut to videos of our robot doing its thing, and we're going to talk about why each part was important. So overall, the goal for the semester was to make a pendulum stand upright. It's an inverted pendulum problem. All right, so the first project that we actually did with the robot was to create a simple oscillator, where without even having the arm or the pendulum attached, we were just going to make the motor oscillate between positive 45 degrees and negative 45 degrees. This turned out to be kind of a complicated problem. It was our first time using a switch, and so we needed to build a Simulink program that would recognize both the angle that the motor was positioned at, and also it's the velocity that it was traveling at. Because it wasn't as simple as saying once you reach 45 degrees, turn back, because then it would just get in this position where it would oscillate back and forth. We need to add memory blocks that would remember what state it was in, what velocity it was traveling at previously, and then it would make a smooth oscillation between 45 and negative 45 degrees.
Another important thing to mention is how we figured out this problem. We used a state table to figure out all of the different states that we wanted for the logic to incur while it was making its decision.
All right, so the next part of our project was to replicate the oscillator, but this time using a simple PID controller. And so the way we built another Simulink program, and the way it worked is it took in an input, either a constant angle position that was desired, or a signal that oscillated between, say, 45 and negative 45 degrees. It would calculate the error between that desired position and where the system actually was, like data from the encoder, and then it was fed into a PID controls. So the P in PID stands for proportional, and that's just simply a gain block. And that is just kind of a standard response. It just multiplies some constant by the error. So it's kind of constant over time, right? And then the I stands for integral response, and this has windup. So over time, the error starts to accumulate, and you get a bigger response if it's not going where it needs to go. So for example, if you were to hold the pendulum away from 45 degrees, if that's the desired angle, over time you would feel more resistance in the robot, and then it would jump farther to try and correct its position.
And next we have D, which stands for the derivative control. Basically, this does nothing in the constant steady state. It only acts when there is a change in the system. So in the case of our oscillator, we have at the endpoints at 45 and negative 45 degrees, where the velocity must change direction, or change magnitude and thus change direction. And so during this change, what the derivative control does is it changes the amount of overshoot in the system. So how far does the system go over the desired value before it returns back, and how quickly does it correct for that error?
This was a really important part of the project because it was a more sophisticated look at feedback that we'll be using later.
Okay, so the next part of the project involved modeling the robot and its links. So to do this, first we went into MATLAB and worked with the 3D plotter to create a simple line representation of the robot. This required using multiple reference frames and learning how to use translation matrices. And so we used basically a single translation matrix for the first portion, and then two translation matrices to both move the second link to the end of the first link as well as rotate it downwards.
So we just looked in a function is we had functions that would do these translations, and then we input two theta values, one for each link, to this function, and we could see that it would rotate all the way around 360 degrees, both 360 degrees in link 1 and 360 degrees in link 2. And then so after we had a function that could input thetas, we wanted to take in thetas from the actual system. So we built another Simulink file that would record the angles from the physical system as while we moved it about, and then plot what we did with the physical system in MATLAB.
Next, we derived the physics engine for the system. This physics engine basically replicated real-world conditions that would happen to the robot as it moves, so gravity, inertia, etc. Basically, we are given some dynamics equations, and then we use those to derive several thetas for the system.
When we talk about thetas, they're just simplifications of that formula, and the thetas represent moments of the system. And so what we did is we had theoretical theta values, and then again, like Ian said, we made a physics engine. And what we did in MATLAB is we started with the pendulum in a position where it was upright. We had an initial condition where it was a little bit tilted, and then the physics engine, when it's representing gravity, showed that pendulum to fall down. That was our test to see if it worked.
So next we worked on figuring out and calculating the Hamiltonian. The Hamiltonian equations were given to us, so we basically went into MATLAB and used those to derive theoretically the theta values that we were talking about. And so the Hamiltonian itself is a matrix representation of the total energy of the system. For our system, that would be the kinetic and potential energy that is basically the movement of each of the links as well as the position of link 2.
So the Hamiltonian is really useful because it can calculate the thetas for a given system. So what we did for our theoretical system is we had a random sinusoidal input to the voltage. So it was just the summation of two sine waves. And we had our simulated system move about randomly. Then from our position data, we were able to use our Hamiltonian to calculate the thetas for that simulated system. And what we found is that the thetas that our Hamiltonian arrived at were the same thetas that we used to calculate the physics engine in the first place. And so that proved that our Hamiltonian was effective. So then what we did is we took that same random voltage input and we applied that to our real system. And we had our pendulum move about randomly. We collected the position data from our encoders, and then we fed that through the Hamiltonian function, and we arrived at the thetas for our actual physical system. So then from there we could do effective feedback, knowing how our system behaves truly. All right, so then after we had our Hamiltonian created and our thetas found, we started to build the actual system that would be used for our final project of getting the pendulum to stand upright. So what we did is we created a subsystem that took in data from the encoders, ran the position data through a transfer function, and then took the derivative of that so that we would have this vector output, the x vector.
And so after we did that, we basically created a multi-port switch that has a function within it that will determine which state we are in.
So what we've drawn here is a representation of the modes of our pendulum system. The first mode is 1, where the pendulum is hanging down and the velocity is small. When in state 1, the pendulum is going to try and swing itself up. And then when it gets up here to this position up top, it's now in state 3, and we'll try and balance. And then if it were to fall, it would be in state 2, where nothing's going to happen. It's just going to fall and wait for the velocity to be small and it to be down here for it to switch back in 1. So if you look over time, we would see this graph. So what we want is this selective way of moving between states where we can only go from 3 to 1, 1 to 2, and 2 to 3.
So after we created our function to select the modes, we decided to use our random sign function to test out our switching function.
We realized though that we couldn't have such a sporadic way of swinging up, and we needed a more controlled method of doing that wouldn't swing the pendulum so randomly. And so we made a feedback subsystem with 2 gains based on a certain percent overshoot that we wanted and a certain peaking time. And then what would happen is we assumed that the desired Q1 for this system was a function of Q2 and the derivative of Q2. So we're able to tweak that linear function to determine the desired Q1, and then our feedback system did the rest and forced the error between our Q actual and the Q desired into 0.
So state 2 did not require anything. So the next part that we worked on was state 3, which is the balancing function. So to create the balancing function, we basically needed to use the Jacobian to calculate and create a state space representation of the system. This was done using the equations that were generated earlier to make the so-called physics engine for the system. And then with the state space representation, you can use state space error controls to optimize the different values of the system.
Right, so once we had our state space representation, we looked at the eigenvalues and we saw that one of them was positive, which meant that the system was unstable. So we needed feedback to make the poles negative so that the system would be stable. And we needed to make sure that they were a negative enough value that the corrections happened quickly. And so we were told that the sweet spot for this was around -5. So we set our poles to -5, -5.1, -5.2, and -5.3. We then used MATLAB to find the gain responses, the gains that would create proper feedback to shift our system to have those poles. So an important thing to note when we were doing this state feedback is that we did it with a point in mind. We set the x vector equal to 0, 0, 0, 0, so that Q1, Q1 dot, Q2, and Q2 dot would all be equal to 0 at the ideal desired position, so that our pendulum would always try and go back to center and being stationary. And it's important to note that 0 for Q1 is located when it's pointed upwards. And also what's important to note is that our K values had a wide range. The largest one was about -12, and it pertained to Q2 because Q2, the position of the pendulum, is the most important and the thing that needs to be stabilized the fastest. Whereas Q1 was the lowest priority, so when we look at our robot, we see that it moves a little bit because it doesn't matter where Q1 is as much as long as Q2 is staying stable.
Yes, and so the next portion was basically using a introduced signal to manipulate Q1, and so to do so, all we had to do was sum in some sort of signal the desired signal that we wanted into the state 3 position, and what this did was add the value into Q1, altering it from 0 to the desired value, and thus moving it to the correct position. And so this was also replicated with the ball sensor, where we just took in the ball sensor's position as a value and then summed it in after manipulating it with a gain so that it would have the correct range, and then with the movement of the ball, the sensor value would change, and thus the Q1 would also change.
And we did the same thing with the sine wave as well, so that was a time-dependent change.
Using the state space linearization method was a relatively efficient way of creating a balance control system for the inverting pendulum robot. It is possible that a logic gate system could have been used to achieve the same effects, but most likely it would have been far more complicated and impractical. As can be seen from the very first lab where we created a simple oscillator using only logic gates, there are much more steps involved in creating a system that achieves the same effects as a transfer function control, and thus, as was said before, it is very impractical to do so.
All right, so that's our whole project. Hopefully we've gone through it in enough detail. But yeah, so over the course of the semester, we were able to make a pendulum that was able to right itself and balance in an upward inverted position.
Yeah, Thank you so much for watching our video, and hope you have a good summer.
It's been a great semester.